Welcome to The Explainer. Today we're kicking off a brand new three-part series on nuclear chemistry, and we're starting by diving deep inside the atom, right into its very core.
So what is it that makes the heart of an atom unstable? We're going to answer that exact question by exploring the particles, the forces, and, the amazing transformations that define the atomic nucleus. Let's get right into it. All right, before we get into the really wild stuff, let's just do a quick refresher on the absolute basics of what's going on inside that nucleus. Okay, so right in that super dense middle of the atom, we've got these particles we call nucleons. It's a bit of a fancy word, but it's really just a catch-all term for the two players in the game: protons, which have that positive charge, and neutrons, which, you guessed it, are neutral. Now, this notation you see here, it's like a secret code for every atom, but it's actually super simple once you see it. The number on top, that's the mass number, and it's just the total count of protons and neutrons added together. The bottom number is the atomic number, and that's only the protons. And that number, that's the atom's identity. It's what makes bromine, bromine. Okay, and here's the plot twist. You might think every single atom of an element is an identical twin to every other one, but that's not quite the whole story. Take lithium, for instance. See these two? They're both lithium, no doubt about it, because they both have 3 protons. That's the rule, right? But look closer. One has 3 neutrons, giving it a total mass of 6. Its sibling over there has an extra neutron, bumping its mass up to 7. And that's exactly what an isotope is. They're atoms of the same element, so they have the same number of protons, but they have a different number of neutrons. Think of them like different trim levels of the same car. They're both the same model, but one's a little heavier. Okay, let's put this to the test. We've got boron 11 here. Now remember, what's the one thing that makes something boron? It has to have an atomic number of 5. That's its ID card. So an isotope of boron also has to have 5 protons. Looking at our options, the only one that fits the bill is B, which has a mass of 10, but crucially has an atomic number of 5. And that one little difference, that extra neutron, or maybe one too few, well, that's where all the action is. Because the universe is all about balance. And if that proton to neutron ratio is off, that nucleus can become unstable. It gets antsy. So when a nucleus is out of whack, maybe it's got too much energy or just the wrong mix of particles, it can't hold itself together forever. It's got to do something to chill out. And that something is to eject a particle or some energy. We call that process radioactive decay. And the stuff that gets shot out, that's radiation. You know, we didn't always know about this stuff. It was a total mystery until the late 1800s when Antoine Becquerel basically discovered it by accident. And then, these absolute legends, Marie and Pierre Curie, just blew the whole field wide open, isolating all sorts of radioactive stuff and figuring out the 3 main ways that it decays. All right, first up, alpha decay. You can think of this like the nucleus is just too big and heavy for its own good. So what does it do? It chucks out a little bundle, a package of 2 protons and 2 neutrons, which, hey, is exactly what a helium nucleus is. Just look at this uranium-238 atom here. It goes through alpha decay. Poof, it spits out that helium nucleus. And what happens? Its mass number drops by 4, and its atomic number drops by 2. It has literally turned into a whole new element, thorium. And notice, the numbers always add up. The top numbers on the right equal the top on the left, and same for the bottom. All right, your turn. Feel free to hit pause and work this one out. What happens when polonium-210 spits out an alpha particle? Well, if you take 4 away from the mass and 2 from the atomic number, you'll find it turns into lead-206. Okay, next we have beta decay, and this one is, well, it's just wild. It's like actual alchemy happening right inside the nucleus. A neutron with no charge suddenly transforms into a proton. But to keep the charge balanced, it has to get rid of something negative, so it spits out a super fast electron, which we call a beta particle. And this shows you just how different it is from alpha decay. Check out radium-228. A neutron flips and becomes a proton. So the total mass, it stays the same. A neutron and a proton have basically the same mass. But because it just gained a proton, its atomic number actually goes up by 1. And once again, it becomes a brand new element, actinium. So, what about thallium-209? Same deal. The mass stays put at 209, but that atomic number bumps up by 1, and boom, it's now lead-209. You're starting to see the pattern, right? It's all just about making sure the numbers balance.
So, okay, who cares, right? Why does this actually matter to us? Well, this chart here tells the story. Those big, bulky alpha particles, they can be stopped by a sheet of paper or even just your skin. Beta particles are a little more persistent, but gamma rays, which are just pure energy, they're like tiny invisible bullets that can go right through you. That's why they're the most dangerous type of radiation to be exposed to.
All right, so we've seen a couple of examples. Now let's just lock in the rules so you can solve any of these nuclear puzzles. And trust me, it's way easier than you might think.
There are really only 2 golden rules you gotta remember. That's it. First, the mass number has to be conserved. The sum of the top numbers on the left has to equal the sum of the top numbers on the right. And second, the atomic number must be conserved. Same deal, but for the bottom numbers. Okay, time to put these rules to the test with a trickier one. Imagine a proton smashes into a molybdenum 100 nucleus. The collision is so intense that a couple of neutrons fly off. So the question is, what's the mystery element that's left behind?
All right, let's do the math. On the left side, what's our total mass? 1 plus 100? That's 101. And the atomic number? 1 plus 42 is 43. Simple enough. So the right side has to match. We know 2 neutrons came out, each with a mass of 1 and a charge of 0. So for our mystery element, its mass has to be 101 minus the 2 from the neutrons, which is 99. Its atomic number is 43 minus 0, still 43. Look up element 43, and you'll find technetium. The answer is technetium-99. See? It all adds up perfectly.
So let's just quickly recap the big ideas from today. The nucleus is protons and neutrons. If you change the number of neutrons, you get an isotope. If that isotope is unstable, it undergoes radioactive decay. And no matter what happens, you can figure out the result by just making sure the top and bottom numbers always balance out. Which leaves us with one big lingering question, right? We know how these things decay, but how can we possibly predict when a specific atom is going to do it? Is it just totally random, or is there some kind of order in the chaos? We'll tackle that very question in part 2, when we explore the amazing concept of half-life. See you then!